Welcome. This video is going to look at the law of multiple proportions, and it sounds a lot like the law of definite proportions, and they're definitely related to each other. So the law of definite proportions says that for any compound, any chemical compound, there has to be a definite or the same proportion of elements in it in order to be that compound. So for example, we looked at water, H2O, and there always has to be about 11% hydrogen and just under 89% oxygen by mass for that to be water. Has to be that percentage of hydrogen, that percentage of oxygen, or it's not water. So the law of multiple proportion looks at what happens when the proportions aren't the same. And so the law is defined as when different compounds contain the same elements, the elements must combine in different ratios to form different substances. Which hopefully this makes sense that if the elements combine in the same ratio, then they're the same substance, but if they combine in different ratios, they're the different substance. So really not that complicated. In other words, we're just saying the same elements can combine in more than one way. Oxygen and hydrogen can combine in more ways and form more things than just H2O or water, although that's by far the one we're most familiar with. So again, mass ratios or mass percents can be used to see if you have the same compound, definite proportions, or different compounds, multiple proportions. So my first example says the mass percents for a mystery compound are 6% hydrogen and 94% oxygen. Is the mystery compound hydrogen peroxide, H2O2, or water, H2O? So how would you solve this? You'd need to find the mass percent of hydrogen and oxygen in hydrogen peroxide and water. And you might remember in the video for law of definite proportions, we already did this for water. And once we have the proportions of each, we can see which one matches our mystery compound. So I'm going to go ahead and start writing my solution in here. So if you want to pause, this would be a good time to do that and try this on your own. I have H2O2. And I can figure out its molar mass because there's 2 hydrogen at a mass of 101 each, plus there's the 2 oxygen at 16 grams each. Remember, I get these numbers from off the periodic table, looking up both hydrogen and oxygen, element 1 and 8. And so my total mass here is 34.02, and I can figure out my percentage of hydrogen by taking 202 over the 3402 times 100%. And then I can also take the oxygen, which is 16 grams, over the 3402 times 100%. And when I do that, I come up with a percentage of 5.94% hydrogen. And then the balance, the 94.06%, is oxygen. And again, I wouldn't have to set up this second proportion. If I felt confident, I could just take 100 minus the 5.94. And then H2O, remember, has just the 2 hydrogen and only 1 oxygen. So its molar mass is 18.02. And when I set up the proportions then, or the percents, it's 2.02 over 1802 times 100%, or 11.21% hydrogen. And again, I can set up the proportion, or I could subtract from 100. I usually go ahead and set up the proportion just to kind of double check my work. And this gives me the 88.79% oxygen. Now, I know when you look at this, you go, well, neither of them matches exactly. But there's always some error, or what we call uncertainty, in our calculations. So 5.94%, that's only 6/100ths, okay? Okay, 6 cents out of a dollar, not a big amount. So yes, this is a match, 6% and 94%. So apparently our mystery compound is hydrogen peroxide. So the law of multiple proportions allows you to compare mass percents to determine if 2 compounds are the same substance or not. Or another mathematical way to decide if you've got the same substance or not is to compare the mass ratio of the 2 elements. And the nice thing about using the mass ratios is it's quicker because you don't have to calculate the percentage of each. So let's look at an example of how we could do this. We're going to look at mass ratios by taking the mass of one of the elements dividing by the mass of the second element, and doing that for each compound we have. Now, it doesn't matter which element I designate as element 1 and element 2, as long as I do it the same for each compound I'm comparing. So as an example, let's look at the mass ratio of oxygen to hydrogen for both water and hydrogen peroxide. Now it's important you read carefully because it says the ratio of oxygen to hydrogen. So this problem is telling me to put the amount of oxygen on top, and for water that's just 16, the mass of the oxygen on the bottom, which is 2.02, and when I divide this in, I get a ratio of 7.92 to 1. And I like to express it as a ratio using the colon here so that I remember I'm comparing oxygen to hydrogen. That's the mass ratio for water. But if I look at the same mass ratio for hydrogen peroxide, now I have 32 grams of oxygen and still just 202 grams of hydrogen, and my ratio becomes 15.8 to 1. So I could look at these ratios, and because I get different mass ratios, again, I would know I have different compounds. And in fact, if I look more carefully, 15.8 compared to the 7.92, if I go ahead and divide those, I get a number very close to 2. I think it's like 1.99. Let me just punch it in my calculator and I'll tell you what it is. 7.92. It's 1.99494. So it tells me that the ratio of oxygen to hydrogen in peroxide is twice as much. So that's my hint that H2O, water, becomes H2O2 when it's peroxide. There's twice the oxygen in there. So that's how scientists use this and apply this. So let's look at an example here. It says carbon reacts with oxygen to form two compounds. Compound 1 contains 4.82 grams of carbon, 6.44 grams of oxygen. Compound 2 has 20.31 grams of carbon, 5.37 grams of oxygen. Compare the oxygen to carbon. So we're being told put oxygen's mass on top, carbon's on the bottom. We don't need to know the molar mass of either one. And then once you have those ratios, what do you know about the formulas for these two compounds? So again, the hints: calculate the mass ratio for each compound by putting the mass of oxygen over the mass of carbon, and then compare the two ratios. And if you want, you can divide the bigger ratio by the smaller ratio to get some idea how their formulas compare. So if you want to try this on your own, this would be a good place to pause the video while I fill in my solution. So for compound 1, I'm told I have 6.44 grams of oxygen and 4.82 grams of carbon, and I was asked to put oxygen over carbon. So I get a ratio of 1.34 to 1, and you don't have to write elements underneath, but I like to so I remember which order it's in, oxygen to carbon. So a little more oxygen than carbon, gram for gram. And then compound 2 has 53.7 grams of oxygen and 20.13 grams of carbon, and this gives me a ratio of 2.67 to 1 oxygen to carbon. And again, it's important that I compare it the same way, oxygen to carbon each time. So what does this tell me about my two compounds? Well, the first thing it tells me is they're not the same compound. These are definitely different compounds because they have different ratios. And besides being different compounds, I can also do a little more investigating here. I can see that the second compound has more oxygen because the number is bigger. And in fact, how much more does it have? Again, if I divide the two ratios, and big over the small, I get 1.99 something, or 2 times as much oxygen in the second compound. So if our first compound happened to be carbon monoxide, CO, my second compound would have to have twice as much oxygen, or be CO2. Finally, I've got one more example to look at where I'm going to kind of give you a taste of both the law of definite proportions and multiple proportions. You have 3 compounds containing tin and chlorine. They're analyzed and the results are below. What conclusions can you make about these 3 compounds? So there's the data you have for each one. And again, my hint is to calculate and compare the mass ratio for each compound. And you can compare chlorine to tin or tin to chlorine, but you must do the same ratio for all three compounds. So next slide here, I'm just going to tell you that I'm going to go ahead and put chlorine on top and tin on the bottom. So if you want to compare to my answer, that may be the way you do it, although you should come to the same conclusion either way you do the ratio. So if we look at chlorine to tin, and again, if you want to pause it and try your own solution first, this would be a good time to do it. Otherwise, chlorine to tin for compound 1, if you look back to the previous slide, it's 3.37 grams of chlorine and 5.63 grams of tin. So this is a ratio of 0.60 to 1, and sometimes your ratio is less than 1. That's okay. It just means there's fewer grams of chlorine than grams of tin. Compound 2, I have 2.98 grams of chlorine to my 2.5 grams of tin. And this time my ratio is bigger than 1, 1.19 to 1, chlorine to tin. And my third compound, I have 8.57 grams of chlorine and 5.12 grams of tin. And my ratio is 0.60 to 1 again, chlorine to tin. And just in case you did it the other way, if you did tin to chlorine, I come up with ratios of 1.67 to 1, 0.84 to 1, and 1.67 to 1. And as I said, we're going to come up with the same conclusions because either way you did the ratio, when we look at it, compounds 1 and 3 have the same ratio, so they must be the same compound. Compound 2 has a different ratio, so it's a different compound. And if you want to look at what makes it different, again, you can look at either set of ratios, but looking at my set of ratios, I can see it has more chlorine than compounds 1 and 3 have. In fact, it has about twice as much chlorine. Or if I look at it from the other ratios over here, I can see it has half as much tin, or the other two have twice as much tin compared to chlorine as compound 2 does. And that's the law of multiple proportions.